MDM4U 7.4 Hypergeometric distributions. A hypergeometric distribution has a specified number of dependent trials having two possible outcomes, success or failure. The random variable is the number of successful outcomes in the specified number of trials. The individual outcomes cannot be repeated within these trials. So, because the individual items cannot be repeated, that's taken without replacement, this is the only probability distribution in this chapter that we've discussed that has dependent trials. So we can think of each of these types of problems fitting this criteria. N is the total number of possible outcomes. So there's N items. And of those items, there's some type of characteristic in which we're going to distinguish the individuals within. They're either considered a successful outcome or an unsuccessful outcome. We're going to let A represent the number of successful items or outcomes. This factor in the numerator represents the selection of X of those successful outcomes. And here, on the right-hand side, N minus A, because N represents the total number of possible outcomes when you subtract A, these are the unsuccessful outcomes, N minus A. And we're making a selection of size R minus X. So if R is our selection size, or the number of dependent trials, taking away X of them, the number from the other group that we consider to be successful that's of interest, then that's the remaining number to make our total selection size. So that explains the numerator for the number of ways in which what we're looking for can occur. That's selecting X people from in our selection from group A, and NS, the number of elements in the sample space. Out of all of the elements, N, we're going to be selecting or choosing R of them. This is all of the ways in which we can do that without any restrictions. So I'm going to take away the definition of probability, and this is what it is specifically for: a hypergeometric random variable. On the right-hand side, what we have is the expected value of a hypergeometric distribution. And the formula, again, the parent definition of expected value of X is the sum of X times the probability of X. This can be simplified to RA divided by N. And we'll be including an additional video on the mathematical proof for that simplification as a bonus. Example, jury selection. Determine the probability distribution for the number of women on a 6-member civil court jury selected from a pool of 8 men and 10 women. So, that being said, a probability distribution. So, if we're looking for a probability distribution, that means that we are looking at each and every single possible value for our random variable. If we choose to let women represent, or the number of women in our selection be the random variable, we have a 6-member civil court jury. So if we're measuring the number of women, we could have 0, 1, 2, 3, 4, 5, or 6 in that selection if we're selecting randomly. So in general, this is going to be our selection, or this is our probability calculation. The probability of X is equal to, out of the 10 women, we're going to choose X of them, because this is just in general for any number, any outcome of the random variable, multiplied by 8, because we consider the women to be successful outcomes, others, men, to be unsuccessful outcomes. So this is 6 minus X. Notice that there's 6 in our selection, and if we take away X of them, we'll end up with our total. We'll further this with a specific example soon. The total number of selections of size 6 that could be made, that's the sample space, is out of all people, 18. That's 10 plus 8, men plus women. Choose 6 of them. That's without restriction. So I'm just going to pick a random example, 2. If we're wondering what is the probability of selecting exactly 2 women, then out of the 10 women, we'll select 2, and out of the 8 men, we're going to select 4. Divided by the total, which is 18, choose 6. This is everyone, choose 6, which is the size of our selection. Notice that in each of these examples, in the numerator, our selection size is still 6. 2 plus 4 is 6. 1 plus 5 is 6. 0 plus 6 is 6. So that's a way to verify that you have a logical calculation. That being said, this represents the distribution of the number of women jurors that we would expect to see if randomly selected. Now, contrast this expected number of women in the jury with this illustration of the probability distribution. The expected value of x is equal to RA over N. So R is the selection size, A is the number of items that we consider to be successful, and N is our population size. So 60 divided by 18 is approximately 3.33. So notice that this is asymmetrical. It's skewed a little bit to the right-hand side. 3.33 is what the average is, the expected value.